Welcome to our comprehensive study of major landforms and the cycle of erosion. In this first segment, we are going to dive deep into marine landforms, exploring how the relentless power of the ocean shapes the very edges of our continents.
The ocean doesn't just wash against the shore, it actively breaks it down. When waves crash into rock fissures, they compress the trapped air, forcing the rock to expand and eventually rupture. Waves also pick up rock fragments, hurling them against the coast like a sandblaster. Finally, the water itself can dissolve soluble rocks, such as limestone, through chemical action.
Let's look at specific erosional landforms, starting with chasms. A chasm is a narrow, deep notch carved into the coastline. It forms when waves relentlessly attack vertical planes of weakness in the rock, cutting inward in a process called headward erosion. Over time, the mouth of this chasm widens through lateral erosion, eventually forming a bay.
As sea waves repeatedly strike a cliff, they erode it laterally, causing the cliff face to gradually retreat inland. This retreating cliff leaves behind a leveled, horizontal plane known as a wave-cut platform. The most intense erosion happens right at the base of the cliff, carving out a distinct notch before the rock above collapses. The steep bank or escarpment that stands tall along the shoreline is known as a sea cliff. These towering structures are the direct result of the continuous undercutting action of the waves at their base, which causes the rock above to shear off and fall into the sea. Not all rocks erode at the same rate. When waves hit a cliff face made of rocks with varying levels of resistance, the softer or highly fractured rocks erode much faster. This differential erosion hollows out the weaker sections, producing deep arched cavities known as sea caves.
Imagine a narrow headland jutting out into the ocean. When waves pound against this narrow wall of rock from opposite sides, they can eventually erode all the way through. The result is a spectacular bridge-like structure spanning the water, which we call a sea arch. Gravity always wins in the end. When the roof of a sea arch can no longer support its own weight, it collapses into the ocean. What remains is a solitary, vertical column of rock standing offshore. Depending on the region, these isolated pillars are called stacks, skerries, or chimney rocks. Sometimes a river flows into the ocean right at a rapidly retreating sea cliff. If the ocean waves are eroding the coastline backward faster than the river can cut its valley downward, the river is left stranded high above the water level. These are called hanging valleys, often resulting in beautiful coastal waterfalls. When a sea cave develops a small opening through its roof to the surface, it creates a fascinating feature called a blowhole or spouting horn. As powerful waves crash into the cave, they rapidly compress the trapped air. This pressure forces a magnificent plume of water to burst up through the hole, often accompanied by a loud roaring noise. Over immense periods of time, marine erosion can level an entire coastal region, leaving behind a flat surface called a plain of marine erosion. If this plain sits very close to sea level, other agents of weathering will continue to smooth it out, eventually converting it into a nearly flat, featureless landscape known as a peneplain. Shifting our focus from erosion to deposition, let's look at the materials the ocean leaves behind. The most familiar depositional landform is the beach. A beach is essentially a temporary covering of sand, gravel, and rock debris that accumulates on top of or right next to a wave-cut platform. Ocean currents and tides often carry sand and debris away from the immediate shoreline, depositing them in long ridges underwater. These submerged ridges are called bars. When a bar grows large enough to enclose a section of coastal water, separating it from the open ocean, that newly sheltered water body is called a lagoon. While a bar remains hidden beneath the waves, a barrier does not. A barrier is simply the overwater counterpart of a bar. It is a ridge of deposited sand and debris that has accumulated enough material to permanently rise above the ocean surface, acting as a shield for the coastline behind it. Sometimes the deposition of sand creates a bridge. When a sandbar forms in such a way that it connects an offshore island directly to the mainland or connects two islands to each other, this specific type of connecting bar is known as a tumbelow. A shoal is a natural submerged ridge or bank made of sand and other loose, unconsolidated materials. Because shoals rise from the seabed to just below the water surface, they are notoriously difficult to spot and pose a significant danger to navigating ships. When coastal currents transport sand and deposit it in a long, narrow ridge extending out from a headland into the open water, we call it a spit. It is anchored at one end and free at the other. If the ocean currents cause the free end of that spit to curve back toward the land, it is specifically referred to as a hook.
A reef is a type of shoal, but instead of loose sand, it is composed of solid rock or coral material near the ocean surface. Natural reefs are incredible biological structures built from the consolidated skeletons of corals. The most famous example is the Great Barrier Reef in Australia, stretching an astonishing 2,300 kilometers. Let's delve deeper into how these coral reefs form. They are created by the accumulation of calcareous skeletons left behind by dead coral polyps. These polyps are tiny, soft-bodied organisms related to jellyfish. They thrive in shallow, warm waters and survive by extracting calcium salts directly from the seawater to build hard, protective skeletons around themselves. These tiny polyps do not live alone. They form massive colonies fastened to the rocky seafloor. When the older polyps die, they leave their hard skeletons behind. New generations of polyps then grow directly on top of these remains. Over millions of years, this continuous cycle builds up massive layers of rock, forming coral reefs, which can even evolve into entire coral islands, like Lakshadweep. Based on their physical structure and relation to the land, coral reefs are classified into three major relief features. These are fringing reefs, barrier reefs, and atolls. Understanding the distinction between these three will give us insight into the geological history of the islands they surround. The most common type is the fringing reef, also known as a shore reef. These grow directly outward from the edge of the land. They are relatively narrow, usually just 1 to 2 kilometers wide, with a very shallow lagoon separating them from the beach. Because the ocean floor drops off steeply on their seaward side, the coral cannot grow further out into the deep, cold water. Next, we have barrier reefs. Unlike fringing reefs, barrier reefs are separated from the shoreline by a wide, deep lagoon. They form extensive, linear structures that run parallel to the coast. While they are less common than other types, they are by far the largest in sheer size, sometimes running for hundreds of kilometers along a continental shelf. The third type is the atoll. An atoll is a roughly circular ring of coral reef that completely surrounds a central lagoon, with no central island visible. These lagoons can be quite deep, ranging from 80 to 150 meters. Atolls are typically found far out in the deep ocean, growing atop submerged features like ancient volcanic cones that have sunk below the surface. Atolls can present themselves in three distinct forms. The first is a true atoll, which is just a circular reef enclosing a lagoon. The second is an atoll that still has a small remnant of an island within its lagoon. The third is a coral, or atoll island, where wave action has deposited enough sand and debris on top of the reef ring to form dry land crowns. If you want to find atolls, you should look to the Pacific Ocean, where they are incredibly common in places like Fiji, French Polynesia, and Micronesia. However, the Indian Ocean also hosts spectacular examples, including the Lakshadweep Islands, the Maldives, and the Seychelles. How do these three reef types relate to one another? Charles Darwin proposed a brilliant theory of subsidence that is still used today. It starts with step 1. A fringing reef grows around a new volcanic island. In step 2, the ocean floor slowly subsides, sinking the island. The coral grows upward to stay in the sunlight, widening the lagoon and becoming a barrier reef. Finally, in step 3, the island sinks completely out of sight, leaving only the circular atoll behind. Now, let's zoom out and look at the coastline as a whole. The coastline is the boundary where the continental landmass meets the sea. These boundaries are constantly being modified, either because the global sea level rises and falls, or because tectonic forces cause the land itself to uplift or subside. Based on these movements, geographers classify coastlines into 5 distinct types. The first type is a coastline of emergence. This occurs when the land is uplifted by tectonic forces, or when the global sea level drops, exposing the former seafloor. Because the shallow ocean floor is now exposed, these coasts are characterized by features like bars, spits, lagoons, and wide beaches. The eastern coast of India, particularly the Tamil Nadu coast, is a classic example of an emergent coastline. Conversely, a coastline of submergence is created when the land sinks, or when the sea level rises, flooding the existing coastal landscape. This drowning of the land creates deep, irregular features, such as rias, fjords, and Dalmatian coasts. In India, the Konkan coast along Maharashtra and Goa is a prime example of a submerged coastline. Let's break down the specific features of submerged coasts, starting with a ria. When a region that has been heavily carved by river valleys sinks below sea level, the ocean floods into those valleys. This creates a highly irregular, branching shoreline known as a ria coastline, much like what you see on the coast of southwest Ireland. A fjord coastline is formed in a similar way but involves ice instead of rivers. In regions heavily eroded by massive glaciers, deep U-shaped valleys are carved below sea level. When the ice melts and the sea rushes in, it creates fjords, long, narrow inlets flanked by incredibly steep, towering rock walls. The coast of Norway is world famous for these dramatic fjords.
Another fascinating submerged feature is the Dalmatian coast. This occurs in areas where mountain ridges and valleys run perfectly parallel to the ocean. When the area is submerged, the valleys flood to become long, narrow channels of water, while the mountain peaks remain above water as chains of elongated islands. The coast of the former Yugoslavia is the namesake for this unique geography.
When a very flat, low-lying coastal plain is submerged, it forms a drowned lowland coast, characterized by shallow waters and series of sandbars enclosing lagoons, like the Baltic coast. More broadly, any submerged coast with highly irregular creeks and inlets is called an indented coastline. These deep, sheltered indentations make absolutely ideal locations for natural harbors.
Finally, we have three other coastline classifications. Neutral coastlines form without any relative change in sea level. They simply grow outward as rivers deposit deltas or volcanoes erupt into the sea. Compound coastlines have a complex history, showing evidence of both submergence and emergence over time. And fault coastlines are created by tectonic activity, where a block of earth drops down along a fault line, leaving a steep, straight cliff face right against the sea. We will explore how other forces shape the earth in our next segment.
Moving right into our next major topographical category, let's examine karst landforms. The term karst actually comes from a province in the Balkans along the Adriatic Sea, where these unique formations are incredibly prominent. What makes a karst landscape so distinct is its underground drainage system. Instead of rivers flowing over the ground, water dissolves soluble rocks like limestone and dolomite, creating a hidden world of sinkholes, fissures, and caves beneath the surface.
To truly understand how these underground networks form, we need to look at the chemistry. Pure limestone is made of calcium carbonate, an organically formed sedimentary rock. When magnesium is present, we call it dolomite. As rain falls through the atmosphere, it picks up carbon dioxide. When it hits the ground and passes through the soil, it absorbs even more carbon dioxide, forming a weak carbonic acid. This acidic solution is what ultimately dissolves the calcium carbonate in the limestone, carving out the rock over time. Not every limestone deposit will develop into a karst landscape. 4 specific conditions must be met. First, the surface or subsurface must contain porous, water-soluble rocks. Second, the rock strata need to be thinly bedded and highly jointed or cracked, which allows the water to easily seep in. Third, there must be moderate to abundant rainfall to drive the chemical weathering process. And finally, a perennial source of water combined with a low water table is required to continuously erode and carry away the weathered rock. Let's look at the specific landforms created by this process, starting with sinkholes. Sinkholes are funnel-shaped depressions on the surface. They develop when cracks in the porous rock are continuously subjected to the solvent action of rainwater, gradually enlarging over time. Because of these depressions, surface streams often completely disappear underground through what we call swallow holes. These sinkholes can vary massively in both size and depth. When multiple sinkholes form close to each other, the ground between them can become unstable. If these adjoining sinkholes collapse, they create a broad open area known as a karst window. This essentially exposes the underground aquifer directly to the surface. Because the protective roof is gone, any water moving over the ground falls straight into this window without undergoing any natural filtration by soil or bedrock.
The merging of sinkholes can happen on an even grander scale. Small depressions dotting the landscape are called dolines. When several dolines merge, they form a long, narrow trench called a uvala. If multiple uvalas coalesce, they create a massive U-shaped valley known as a polye. Interestingly, if a surface stream flows into one of these valleys and completely loses itself underground, the valley is referred to as a blind valley. Perhaps the most famous karst features are caverns. A cavern is simply an underground cave formed within a limestone stratum. They are carved out by a combination of the chemical solution action of water dissolving the rock and the mechanical friction of rock debris and pebbles being washed through. If you are looking for examples in India, spectacular caverns can be found in Bastar, Dehradun, and the Shillong Plateau. Caverns are not permanent structures. Over geological time, the roof of a cavern may become too thin to support its own weight. When a large section of a cavern collapses, the portion of the roof that manages to remain standing forms a natural arch or bridge. These dramatic stone arches are literal windows into a cave system that used to exist there. In a karst valley, you might be following a stream only to see it vanish right before your eyes. The water often gets lost through deep cracks and fissures in the stream bed. We call these sinking creeks. If the tops of these fissures are wide open and visible at the surface, they are specifically referred to as bogus. Inside these caverns, the dripping water creates beautiful formations. As water containing dissolved limestone seeps through the cave roof, it evaporates, leaving behind a tiny deposit of calcium carbonate. Over time, this builds an icicle-like structure hanging from the ceiling called a stalactite. When the drops hit the floor and evaporate, they build a thicker, flatter mound rising upward, called a stalagmite. Eventually, a stalactite and stalagmite might meet, forming a solid, continuous pillar known as a column. As the main stream in a karst landscape erodes deeper into the earth, the local water table drops with it. Because the water table is now lower, the tributary streams start draining underground instead of flowing on the surface, eventually drying up completely. These dried-up riverbeds are called dry valleys, or bournes. Because they lack water, they stop eroding downward, leaving them stranded high up on the side of the main valley, which is why they are also called hanging valleys. Just like river systems, karst landscapes go through a distinct cycle of erosion, starting with the youth stage. In this early phase, water still flows mostly on the surface of the initial limestone layer. As the upper impervious rock is gradually eroded away, the first dolines, sinkholes, and swallow holes begin to form. At this point, the underground drainage system is still incomplete, and no large caverns exist yet. As time passes, the landscape enters the maturity stage. Here, underground drainage reaches its absolute maximum. Surface streams are rare, limited to short creeks that quickly vanish into swallow holes. This is the era of extensive, complex cavern networks. As we move into late maturity, these features actually begin to decline. Cavern roofs collapse to form karst windows and massive uvulas, leaving only detached, isolated towers of the original limestone upland standing out, which we call hums. Finally, the landscape reaches old age. By this point, there has been a massive, large-scale removal of the limestone mass. The complex underground networks have completely collapsed and eroded away, leaving behind a relatively flat karst plain. Because the porous rock is mostly gone, surface drainage actually reappears, flowing around a few isolated hums, the very last remnants of the original limestone terrain. This cycle of erosion perfectly sets the stage for our next major topic, where we will look at how ice, rather than water, carves the earth. Moving right along, let's look at the immense power of glaciers. A glacier is a massive body of ice moving slowly across the landscape, averaging just a few meters a day. But don't let the slow speed fool you. Glaciers are charged with heavy rock debris, which acts like sandpaper, giving the moving ice incredible erosional power. There are 4 main types of glaciers we need to understand. Continental glaciers are massive ice sheets found in places like Antarctica, Greenland, and Iceland. Ice caps are smaller covers of snow and ice on mountain peaks. Piedmont glaciers form a continuous ice sheet at the base of mountains, like in southern Alaska. Finally, valley or alpine glaciers flow down high mountain valleys, such as those in the Himalayas. As these massive ice bodies move, they act like giant bulldozers, carving out distinct glacial erosional landforms. The immense weight and grinding action of the ice completely transform the original landscape, leaving behind a signature set of features that we can identify long after the ice has melted. Let's break down these erosional features, starting with the cirque, sometimes called a corrie. A cirque is a hollow basin cut directly into a mountain ridge. It features steep slopes on 3 sides, an open end on the 4th, and a flat bottom. When the glacier eventually melts, water often pools in this flat basin, creating a beautiful mountain lake known as a tarn. Next is the glacial trough. Before a glacier moves through, a river might carve a sharp V-shaped valley. But because glacial mass is heavy, slow-moving, and solid, its erosional activity is uniform both horizontally and vertically. This widens and deepens the valley, transforming it into a steep-sided, U-shaped trough. Because the main glacier is so massive, it carves a very deep trough. But what about the smaller tributary glaciers feeding into it? These smaller glaciers lack the mass to cut as deeply as the main one. When the ice melts, these tributary valleys are left suspended high above the main valley floor, creating what we call a hanging valley, often featuring spectacular waterfalls. When 2 adjacent cirques erode backwards toward each other, they carve out the rock between them.
This creates a steep-sided, sharp-tipped ridge known as an arête. It looks like the jagged edge of a serrated knife separating two glacial valleys.
If glacial activity cuts into a mountain from more than two sides, those radiating cirques erode headward to form a sharp pyramidal peak called a horn. Some of the most famous mountains in the world, including the Matterhorn in the Alps and Mount Everest in the Himalayas, are actually horns formed by this intense glacial erosion.
Finally, at the coast, we find D-fjords. A fjord is a steep-sided, narrow entrance-like feature where a glacial trough meets the sea. As the glacier retreats and sea levels rise, the ocean floods the deep U-shaped valley. These are incredibly common in places with heavy historical glaciation, like Norway, Greenland, and New Zealand.
Now, here is a fascinating question, often seen in advanced exams. Why are the world's highest mountains mostly located near the tropics? It comes down to the snow line. Glacial erosion is incredibly strong. In colder climates, the snow line is low, meaning glaciers form at lower altitudes and aggressively erode the peaks. Mountains generally only rise about 1,500 meters above their snow line before erosion caps their height. In contrast, at low latitudes near the tropics, the atmosphere is much warmer, so the snow line is very high. Around the equator, the snow line might be at 5,500 meters. Because the aggressive glacial erosion doesn't start until that high altitude, the mountains are able to grow much taller, often reaching up to 7,000 meters before glacial erosion limits their upward growth. Erosion is only half the story. When a glacier eventually reaches lower, warmer altitudes and melts, it drops all that rock and debris it was carrying. This creates an entirely new set of features known as glacial depositional landforms. The broad area where this melting and deposition occurs is called an outwash plain or a till plain. As the glacier reaches its lowest point and melts, it leaves behind a stratified or layered deposition of material consisting of rock debris, clay, sand, and gravel. The most common depositional feature is the moraine, which is a general term for the rock fragments and gravel carried and dropped by a glacier. Their names depend on their position. Lateral moraines form along the sides, medial moraines form in the middle when two glaciers merge, recessional moraines mark temporary standstills, and terminal moraines mark the furthest edge of the glacier's advance. An esker is a fascinating feature. It looks like a winding, twisting embankment running across the till plain. It is a ridge of unassorted rock, gravel, and clay that was deposited by meltwater streams flowing through tunnels underneath the glacier. Because they form natural, elevated pathways, eskers are often used for making roads. Next, we have kames and kame terraces. A kame is an irregularly shaped hill or mound of sand and gravel that accumulates in a depression on top of a retreating glacier and then drops to the ground when the ice melts. Kame terraces form when sediment accumulates in lakes trapped between the glacier ice and the solid valley side. Drumlins are distinct inverted boat-shaped mounds of deposited material found in a till plain. They have a steep side and a gently sloping side. Drumlins are highly useful for geologists because their elongated shape gives a clear indication of the direction the glacier was moving. Finally, we have kettle holes. These form when large blocks of ice break off the retreating glacier and get buried in the outwash plain. When those buried ice blocks eventually melt, the sediment above them collapses, forming a local depression or basin. If they fill with water, they become kettle lakes. Just like rivers, glaciers go through a cycle of erosion. In the youth stage, the landscape is marked by the inward cutting activity of ice in a cirque. Aretes and horns are just beginning to emerge as the ice carves into the rock, but hanging valleys are not yet prominent. Moving into the maturity stage, the landscape becomes much more dramatic. Hanging valleys start emerging as the main trough deepens. Opposite cirques cut closer to each other, sharpening the aretes, and the main glacial trough acquires a regular, graded, stepped profile. Finally, in the Old Age stage, the landscape is dominated by the emergence of a massive, fully formed U-shaped valley. The erosional work is largely done, and a prominent outwash plain develops, featuring all the depositional landforms we discussed: eskers, kame terraces, drumlins, and kettle holes. Next, we will contrast this ice-driven landscape with the arid landscapes shaped by wind and sparse water. Let's dive into arid landforms and the cycle of erosion. Arid regions are simply areas that receive very little rainfall. When we talk about these regions, we are generally referring to both true deserts, which are extremely dry, and semi-arid regions, which get slightly more moisture but are still largely dry and sparsely vegetated. You might think that because deserts are dry, water doesn't play a role in shaping them. But actually, water is a major erosive force in arid lands. Because there is very little vegetation to hold the soil in place, when occasional heavy rainstorms do occur, the water runs off rapidly, carving out distinct and dramatic landforms. The smallest scale of water erosion creates what we call a rill. A rill is a very narrow and shallow channel cut directly into the soil. As runoff water flows over the bare ground, it concentrates into these tiny streams, picking up loose particles and carving these miniature drainage networks. When rills merge and water continues to flow with more force, they grow into gullies. A gully is essentially a larger ditch or a small valley created by running water. They are much bigger than rills, often measuring several meters to tens of meters in both depth and width. Once a gully forms, it channels even more water, accelerating the erosion process. Moving up in scale, we have ravines. A ravine is a landform that is narrower than a canyon, but larger than a gully. It is typically the product of aggressive stream cutting, specifically downcutting, where the water erodes vertically into the earth. They are deep, steep-sided, and represent a more advanced stage of linear fluvial erosion. At the largest scale of these water-carved channels, we find canyons and gorges. A canyon is a massive, deep, narrow valley with very steep sides, carved over long periods. A gorge is very similar to a canyon, but the key difference is that a gorge is almost always steeper and narrower, often with nearly vertical walls plunging straight down to a river. When occasional intense rainstorms hit an area with weak sedimentary rocks, the resulting rills, gullies, and ravines can completely tear up the landscape. This extensive linear erosion creates what we call badland topography. It's a rugged, difficult terrain to navigate, characterized by a maze of steep slopes and deep channels. A famous example of this is the Chambal ravines. Now let's look at some larger basin features. In dry, mountainous regions, you often find flat valleys or basins completely surrounded by mountains. These enclosed intermontane basins are known as bolsons. They act as a central collection point for any water and sediment washing down from the surrounding high ground. Inside these bolsons, small streams flow down from the mountains and pool in the lowest part of the basin. Because there is no outlet, this water forms a temporary shallow lake called a playa. In the intense desert heat, this water quickly evaporates. When it does, it leaves behind all the dissolved minerals, creating a flat, white, salt-covered surface known as a salina. At the base of the mountain surrounding a bolson, you will find a pediment. A pediment looks very much like a gently sloping plain at the foot of the mountain. However, it is fundamentally an erosional landform. It is a solid, rock-cut surface that has been worn down and planed off by the retreat of the mountain front over time. While a pediment is erosional, a bajada is depositional. As water rushes out of mountain canyons, it dumps its load of rocks and sediment at the base, forming an alluvial fan. When several of these alluvial fans merge and blend together side by side along the mountain front, they create a continuous, moderately sloping depositional plain called a bajada. Bajadas sit right between the rocky pediment and the flat playa. While water is powerful, wind, or aeolian erosion, is the other major sculpture of deserts. Wind erodes in three main ways. First is deflation, which is simply the wind lifting and blowing away loose, dry dust and sand. Second is abrasion, where the wind acts like sandpaper, blasting airborne sand grains against rock walls to grind them down. Finally, attrition occurs when the airborne sand particles crash into each other, wearing themselves down into smaller, rounder grains. Let's look at the results of deflation. When the wind continuously removes loose particles from a specific area, it scoops out a depression in the ground. These hollows are called deflation basins, or blowouts. While many blowouts are quite small, if the wind is persistent and the soil is loose, they can grow to be several kilometers across. Abrasion creates some very distinct shapes, most notably the mushroom rock, also known as a rock pedestal. Because wind carries most of its abrasive sand close to the ground, it erodes the base of a rock outcrop much faster than the top. Over time, this undercutting leaves a large bulbous top balanced on a narrow stem, looking exactly like a giant stone mushroom. Sometimes you'll see a massive, isolated hill or a small mountain rising abruptly out of an otherwise completely flat plain. This is called an Inselberg or a Monadnock. It is a remnant of a much older landscape. The surrounding softer rock has been entirely eroded away over millions of years, leaving only this core of highly resistant rock standing alone. Differential erosion, where soft rock erodes faster than hard rock, also creates demoiselles. These are tall, slender rock pillars. They form when a layer of hard, resistant rock sits on top of much softer rock. As the surrounding soft rock is washed and blown away, the hard rock acts like an umbrella, protecting the column of soft rock directly beneath it, resulting in these striking pillars. Similar to demoiselles, a zoygan relies on alternating layers of hard and soft rock, but usually in horizontal layers. When weather and wind attack these layers, the softer rock underneath is eaten away much faster than the hard cap rock on top. This creates a table-shaped landform, often with deeply undercut sides standing above the desert floor. If you look at a desert from above and see long parallel ridges of rock, you are likely looking at yardings. Unlike zougans, yardings are carved into vertical bands of hard and soft rock. The prevailing winds act like a gouge, scouring out the softer rock to form long trenches, leaving the harder rock standing as streamlined ridges that point directly along the path of the wind. Wind abrasion can also punch right through solid rock. Powerful winds carrying sand can continuously scrape away at weaker spots in a rock face, eventually boring a hole completely through to the other side. This creates a wind window. As the wind continues to abrade the edges of this window, it widens over time. Eventually, the opening becomes so large that the remaining rock forms a spectacular arch, known as a wind bridge. Wind doesn't just erode, it also deposits the material it carries. This brings us to arid depositional landforms. The smallest of these are ripple marks. As wind blows over loose sand, it moves the grains through a bouncing action called saltation. This turbulent flow of air organizes the sand into small, rhythmic, wave-like ridges on the surface, very similar to the ripples you see underwater at the beach. When wind deposits sand on a larger scale, it builds sand dunes. Dunes are simply heaps or mounds of wind-blown sand. They can vary wildly in size. Some are just a few meters tall, while the massive megadunes found in deep deserts can tower several hundred meters high and stretch for 5 to 6 kilometers in length. The shape a dune takes depends entirely on wind direction and sand supply. Let's look at the different types of dunes. First are longitudinal dunes, also known as linear dunes. These form parallel to the direction of the wind. They have a gentle slope on the side facing the wind and a steep drop-off on the sheltered leeward side. You'll commonly find these massive, long ridges in the heart of major trade-wind deserts like the Sahara, the Australian desert, and the Thar Desert. In contrast to longitudinal dunes, we have transverse dunes. These dunes form when there is an abundant supply of sand and a constant wind direction. The sand piles up in long ridges that run perpendicular, or transverse, to the direction the wind is blowing. They look like giant stationary ocean waves made of sand. Perhaps the most classic desert dune shape is the barchan. Barchans are crescent-shaped dunes that form where sand supply is somewhat limited. The wind pushes the edges of the dune faster than the thicker center, creating two horns that point downwind. The windward side is a smooth convex ramp, while the sheltered leeward side is a steep concave slip face. Parabolic dunes are also curved, but they are essentially the reverse of a barchan. They are U-shaped, but their horns point upwind into the wind. This usually happens because the arms of the dune are anchored in place by sparse vegetation, while the wind blows the center of the dune forward. They tend to be much longer and narrower than barchans. When the wind in a desert doesn't blow from just one direction, but shifts around and comes from multiple directions, it creates star dunes. These are complex, massive dunes with a high central peak and 3 or more arms radiating outward. Because the wind keeps pushing sand toward the center from all sides, star dunes tend to grow taller rather than migrating across the desert floor. Finally, we must talk about the finest particles the wind carries, dust and silt. When the wind blows across a desert, it picks up these incredibly fine particles, which can include quartz, mica, and even organic material. The wind carries this dust far beyond the desert edges and drops it in massive, thick blankets over the land. This layer of fine, wind-blown silt is called loess. You can find extensive loess deposits in places like northern China, the American Great Plains, and Central Europe. What makes loess so important is that it develops into some of the most incredibly fertile agricultural soil on the planet. Because it is made of fine wind-ground minerals, it is packed with nutrients. It drains water beautifully and is very easy to plow and plant. Even though it can erode, it does so slowly enough that civilizations have thrived on it. For instance, Chinese farmers have been successfully cultivating the thick loess soils around the Yellow River for well over 1,000 years. To wrap up our discussion on arid landforms, remember that both water and wind are master sculptors in dry environments. Despite the lack of rain, sudden water flows carve deep ravines, canyons, and badlands, while depositing material in basins. Meanwhile, the wind acts as a constant abrasive force, carving out unique rock formations and sweeping up sand and silt to build massive dune fields and lay down incredibly fertile loess plains. That concludes our look at the cycle of erosion in arid landscapes.